Okie dokie. Right. It's split into three topics. Particle physics. We'll be talking about constituents of the atom, constituents of the nucleus. I'm just hoping that my little pen doesn't run out of battery. I should have been charging it during the break. We'll then talk about radioactive decay, go through the mass of that, and then last we'll talk a bit about fusion and fission and nuclear physics. But first, we'll talk a bit about particle physics, the standard model, and so on, and so on forth. Right, the nucleus. Our knowledge of the nucleus really kicks off with Rutherford's famous gold leaf experiment. And the setup is as follows in the diagram. We have a scintillating zinc sulfide screen detector. When I say scintillating, I mean that if any particles strike it, it produced light. A gold foil, which is only a few atoms thick. Some people say, why use gold? Gold is very malleable. You can hammer it into very, very, very thin sheets, which is genuinely only a few atoms thick. So that when we fire an alpha particle at it, and we've got our source inside the lead box with just a thin opening so we can direct the beam towards our gold foil. The idea is that we're only going to, our alpha particle will hit one atom only before then being deflected off. So what were the results? As you can see in the diagram, most of them passed straight through. Some of them were deflected by severe angles, and some, most importantly, were reflected at reflex angles, so reflected back on themselves. So most alpha particles pass straight through. The conclusion to draw from that, therefore, is like this trajectory here, is that most of the atom is actually empty space. This goes against the plum pudding model that existed before, where it was posited that the atom is filled with this sort of sea of positive charge, this big blob of positive charge with just a few currents of, not currents as in electric currents, but currents as in raisins, a few little blobs of negative charge. But no, the fact that most alpha particles passed through rather than either being absorbed or being reflected elsewhere implies that most of it's empty space. Some were, it was only 1 in 10,000, mind you, but some alpha particles were deflected by angles of more than 90 degrees. This implies that the nucleus is positively charged. Okie dokie, we now know, and so we're left with, rather than the plum pudding model, we are left with this picture of the atom, which we call the Bohr model, named after Niels Bohr. The nucleus is roughly 10 to the minus 15 meters across, 1 femtometer. And we have electrons orbiting our nucleus. The nucleus is made of two types of nucleons. My tongue gets very confused sometimes when I'm talking about this subject. We have neutrons, nucleons, protons, hadrons, baryons, and all that. It all ends in on, and they start to sound a little similar. Protons, positive charge, equal to the positive charge is plus E, so the same charge as an electron, but opposite sign. And the mass is equal to 1 U, or roughly 1 U, where U is the mass of a nucleon, mass of a neutron, and that's roughly 1.66 times 10 to the minus 27 kilos. Protons and neutrons have pretty much the same mass, but not quite the same. Neutrons are very slightly more massive. Nuclei but for the purpose available, it doesn't really matter. I think the difference is in the fourth significant figure. In this red box, nuclei with different numbers of protons are different elements. Yes. So we've got our standard notation here for a given nucleus. The number in the bottom left is the atomic number, or proton number. And as the name suggests, it indicates how many protons you have. This number here is your nucleon number. Some of you may say, well, hang on, isn't it relative atomic mass? Technically no, because relative atomic mass can form. If you look at the periodic table, or fancy versions of the periodic table, you'll notice that carbon doesn't have, the number isn't a whole number, it'll be like 12.022 or something like that. That's relative atomic mass because that's a weighted average of all the isotopes that occur, weighted according to how often you find them in nature. So, you know, if I'm being pedantic, that's it. And then this is just the symbol for whatever element you're talking about. The element being determined by the atomic number. Okay, that's what this red box says. Neutrons, they're uncharged, so no charge, and they have pretty much the same mass as the proton. And nuclei with different numbers of neutrons, but the same number of protons are different isotopes. Keyword. Okay, so if you change the number of protons, you've got a different element entirely. If you change the number of neutrons, you've got an isotope of that element. And if you change the number of electrons, you've got an ion. You've got a charged ion if you remove an electron. And just for the avoidance of doubt, the nucleon number is the number of protons plus the number of neutrons. What's the, you know, in other words, it's the total population of the nucleus. Okay, in 1904, J.J. Thomson proposed the plum pudding model as a way of explaining the structure of the atom. It stated that electrons occupied a region or soup of positive charge, as shown in the diagram. This was a generally accepted model for the atom before Rutherford's apple particle experiment. Describe with reasons the results that Rutherford would have expected from his experiment, and explain how his actual results showed the plum pudding model was incorrect. This is a fairly standard question, not necessarily common. It's not going to be in every year's exams, but it does come up from time to time. There's the diagram. There's the plum pudding model. I shouldn't laugh at it. You know, I always feel a bit condescending. You know, they didn't know. They hadn't done the experiments yet. We would be no better. Okay, so the expected results would be that particles would shoot through the foil with only a minimal amount of deflection. It's because the foil's thin, so the positive charge and the mass wouldn't be concentrated enough to affect the alpha particles. This soup is so thin that you'd expect, you know, maybe the particles would go through, but they'd be minimally deflected. It's not sufficient. Instead, they found that, well, okay, they found almost all the atoms passed through unaffected, with a minority being completely deflected. Okay, so both of those are unexpected. They were expecting pretty much all of them to be like a little deflected, but instead there were plenty that were just totally unaffected. And they were not expecting any to be completely deflected, which means that there must be some high concentration of charge somewhere in the atom. And that's the nucleus. This means most of a particle's mass is concentrated at a small point in the atom. And if you once you've deduced that there's a high concentration of charge somewhere, it stands to reason that the rest of the space is not very high concentrated, i.e. it's empty. Also means this small point contains all the atom's charge. It is not even spread across. Okay, I don't quite agree with the phrasing there. You know, obviously the electrons also have charge. The small point contains all the atoms' positive charge. Maybe I would allow. Right. There are three types of fundamental particles. So we talked about the nucleus. Let's go even deeper. The nucleus is not a fundamental particle. We can break it down even further. So that's what we mean when we say fundamental. Cannot be broken down. Once upon a time, J.J. Thomson, indeed, before he came up with his plum pudding model, thought that the atom. I don't know why I singled him out. Physicists in general thought that the atom could not be broken down. In fact, the name atom itself means sort of unbreakable. So it's a little bit ironic. But alas, we now think these are fundamental. Maybe we'll be proved wrong at some point, but who knows? In the top left, in the purple corner, there are the quarks. There's 6 types. So sort of 3 families. You've got up and down, charm and strange, and then top and bottom. We don't tend to talk about these so much. Some physicists actually call them truth and beauty, just in case you're feeling poetic. But top and bottom is by now by far the most widely accepted denomination. And these quarks can be used to assemble hadrons, which require 3 quarks, or mesons, which is a quark and its anti-quark, its antiparticle. Hadrons can also be formed from 3 anti-quarks. But for example, proton is a hadron. It is an up quark, and a down quark. A neutron, if you forget, it's got no charge. It's a dud. So it's up quark, down quark, DUD. Leptons in the green corner. So the quarks you don't find on their own. They always combine to form hadrons or mesons. They don't occur naturally on their own. Leptons do occur on their own naturally. And again, there's 3 families. There's the electron family, the muon family, and the tau family. And these all have the same charge. The difference between them is their mass increases. So a muon is kind of like a heavy electron, and a tau particle is like a heavy muon. So they all have negative charge. The electron, muon, and tau all have negative charge, and then you have their neutrinos, which have barely any mass and have no charge. Their name implies they're neutral, and that's correct. Okie dokie. And then last you have the bosons. These are associated, each of them, with a fundamental force. So the gluon is associated with strong nuclear force. It sort of acts like a glue that glues your quarks together. Photon is associated with electromagnetism. And then you've got your Z bosons and W bosons, which are used in various nuclear forces as well. Fab. Right. Hadrons are particles. Yeah, right. So I said that quarks could be combined into hadrons and mesons. Hadrons contain quarks, and they feel the strong nuclear force. Quarks are fundamental, but they can't be found on their own. You have to break up hadrons or mesons to find them. So mesons, quark, antiquark, pair, hadrons, 3 quarks or 3 antiquarks. So for example, a pion plus meson is an up, it's down. Okay. On the right, you've got a table of the quarks and their charges. You'll see they're in thirds because to form hadrons, they always They're always in threes. And whatever hadron or meson you form, it needs a whole number of charges, because charge is quantized essentially outside of hadrons, mesons, and leptons. Remember, we said that I forget whether it was today or yesterday. We said the charge of an electron is the sort of fundamental charge. You can't all charged objects have to have a charge that is an integer number of the charge of an electron. And that's true for hadrons and mesons as well. You can't have something that has a charge of, plus 2/3 E floating around on its own. Okay. Sorry, so when I said hadrons and mesons, hadrons are themselves split. So hadron is the collective term for mesons and baryons. So both mesons and baryons are types of hadrons. Hadrons can either be mesons or baryons. And these are the baryons. So I'll rewrite that here. Quark, 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 or quark, antiquark, antiquark, antiquark. Okay, so for example, we've already done the proton, is up, up, down. Zero. Every quark and lepton in the standard model has a corresponding antiparticle, so the table gets even bigger. You can kind of double up the standard model. Antiparticles have the same mass, but equal and opposite charge to their corresponding particle. So an antiproton which is formed of the same quarks, but they're antiparticle versions. So instead of up, up, down, it is anti-up, anti-up, anti-down. And the antiproton as a whole has the same mass as a proton, but a negative charge. When antiparticles meet their corresponding particles, they annihilate, which means they disappear. So if I've got in the red corner, I've got good old electron, and we've got an anti-electron. You can tell it's an anti-electron because the hat. That's what it means, a little anti. However, the anti-electron is the only antiparticle to have its own special name. That special name is the positron. Electron versus positron. Now it really does feel a bit like Transformers. They annihilate, their mass is destroyed, and released instead are 2 photons. Why not 1 photon? Well, momentum still has to be conserved. We said momentum's always conserved, and even at this scale, even in this slightly wacky corner of physics, it is still the case. So now that's plus E. Okay. Antiparticles are indicated by their corresponding particle symbol overlined. Okay, exam question. For each of the following quark combinations, write the charge of the respective particle. Okay, and if it's a baryon, antibaryon, or meson, we could probably do this on this page. This is quite a nice, 3 marks. This is pretty juicy. It does mean, however, you're probably going to need to remember. I think your formula sheets perhaps have some information about the quarks. I can't remember how much though, so do check. And it depends on your exam board. Right, so identify the type of particle. The first only has 2, it's a quark antiquark particle, so it's definitely a meson, whereas these are going to be baryons. Or this will be a baryon, this will be an antibaryon because it's made out of antiparticles. It's not too complicated. The up quark has a plus 2/3 charge. Down quark has a minus 1/3. We also have up is 2/3, down is minus 1/3. You also have some strange quarks and also some bottom quarks. The good news is that top and bottom follow the same pattern. So top has 2/3, bottom has minus 1/3, and the same for charm and strange. Okay. Okay, so the first one is a meson. I said up is plus 2/3, therefore anti-up is minus 2/3. Down, I already said was minus 1/3, so the total is -1. Sweet. Right, is a baryon. Up gives us 2/3 times 2, that's 4/3. Our strange will give us minus 1/3, that's +1. Okay. This is an antibaryon, so the strange quark. Strange has a charge of minus 1/3, so the anti-strange has plus 1/3. The bottom has minus 1/3, so the anti-bottom will have plus 1/3. So we get 1/3 plus 1/3 plus 1/3, and so this will also have a charge of +1. But all three of them had the same charge, +1. Right, radioactive decay. Nuclear radiation. Random process. We've got it can occur in several types. We've got alpha, beta, positive and negative, and gamma. Those are the 3/4 you need to be aware of at A level. In each case, it's a different particle, or it's not. In gamma's case, it's not even a particle, or it's a. I guess you can argue it's whatever. It's a photon slash a wave, light. And in case alpha particles are heavier than any of the other types of decay. They are formed of a helium nucleus, i.e., 2 protons, 2 neutrons, and no electrons. So it truly is just the nucleus of a helium atom. This tends to mean that the range of alpha radiation is very short, because you've got such a heavy particle, and it's very ionizing because it's got a charge of 2+. It's got 2 protons. It's absorbed in air within a couple of within 10 centimeters or so. So it's not too bad. Right. Decay equation. If I've got an unstable nucleus here and it emits an alpha particle, the changes are, well, whenever you read these nuclear equations, treat it as 2 separate additions / subtraction sums. The numbers on the top all need to add up to each other. A equals 4 plus A minus 4. Z equals 2 plus Z minus 2. A, Z, and the charge all need to be conserved. This is a strange order to cover them in. But so much for alpha decay. Gamma decay, photons are released, gamma particles, the high energy gamma ray photons. So, this doesn't really affect the number of particles in the nucleus. It's just released sort of in concert with the other decays. Alpha decay happens or beta decay happens, and if you've got any energy left over, if you'll normally represent it with an asterisk, just to say it's in an excited state. And so you release a photon. Okay, we then have the beta brothers, 2 types of beta decay. Beta positive decay will end up releasing a positron. Beta negative will end up releasing an electron. Okay, so in beta positive, we start with a proton. Remember that charge needs to be conserved on both sides. So we start with a charge of +1. We'd better end with a charge of +1, so we know it's a positron that's coming out here. We also need to conserve. I don't know if we will be covering conservation laws in a moment, but at any rate, I'm happy to remind you the things that need to be conserved in all nuclear reactions is charge, baryon number, and lepton number. But remember that lepton number is specific to each family of leptons. So electron lepton number has to be conserved, as well as muon electron number, as well as tau electron number. Okay, so we started with a baryon before, so we need a baryon afterwards. So we've got a neutron, because that ticks the box of charge and baryon number. And a lepton number needs to be conserved. We had no leptons to start off with. Afterwards, we have got ourselves an anti-lepton. So we need ourselves a plain old lepton to balance things out. So we have a neutrino, and it's technically an electron neutrino. Okie dokie. In terms of the quark transformation, then, you start with a proton, which is up, up, down, and you end up with a neutron, among other things, which is up, down, down. So one of my up quarks is becoming a down quark. So this is the sort of quark level. But just for clarity, charge, baryon number, and lepton numbers must be conserved. And that is for all these, for all nuclear interactions. Neutrinos are uncharged particles which carry away energy in the decay. Yep, much like the photon does for gamma. If you've got a little bit of extra energy left over, you've got a little neutrino. Little cute fella. Right, beta negative. Instead of starting with a proton and ending with a neutron, we start with the neutron and with a proton. Okie dokie. We start with no charge, but we produce a positive particle and a negative particle, which balance each other out. We start with a baryon. We have a baryon afterwards. Great. We start with no leptons, and then we produce a lepton. So we need an anti-lepton, anti-neutrino. And it is an anti, is an electron anti-neutrino. Okay. And in terms of quarks, we start with a down quark and we get an up quark. Great. Okie dokie, exam question. Particle X decays to particle Y through a combination of multiple alpha and beta decays. Complete the combined decay equation to show all byproducts produced in the decay, assuming that any particles have cancelled with the respective antiparticle if present. You do not need to include photons in your equation. How exciting. Right. These questions do come up from time to time where you've got like a series of decays. The key is to recognize what the impact of each type of decay is. So for an alpha decay, you will be subtracting. So, you start with 230, 91. If you choose to, you've got two moves you can make, or three moves you can make. You can do alpha, in which case you subtract 4 off the top and 2 off the bottom. You can do beta negative, in which case you will be beta negative, you'll be starting with a neutron and adding a proton. So there's no change at the top, stays the same, but you'll be gaining a proton. Okay. In fact, and then beta positive, similar. no change on top, but you will be losing a proton. V. Okay, so those are the 3 moves you can make, and you can make them as many times as you like. We start at 230. We need to reach 226. Let's not worry about that too much. More important, perhaps, is we start at. Actually, no. Let's start on the top, because we know the beta decays. They don't affect the nucleon number. So by looking at the top numbers, well, it only goes down by 4. So there must therefore only be 1 alpha decay. That's a must. So let's do it. Beta decays do not affect A value for the particle. In fact, I've just explained what that sentence says. So there's a bit of redundancy. Right, so do your alpha decay. The only product is an alpha particle, and the result is 22689. Okay, so what we need remaining is we need to subtract 2 off of this. What decay is going to help us do that? It's beta positive decay. So 2 beta positive decays. Beta positive decay produces 2 positrons and 2 electron neutrinos. And that's the answer to the question. So a nice little exercise in deduction. Hopefully not too aggressive. Okay, radioactive decay. How are we doing for time? We're aiming to finish at 5:15. But if we finish earlier, I promise we'll wrap up a little earlier. Radioactive decay is spontaneous and random. Those are the 2 words. If you're asked an exam, oof, what's going on with radioactivity? Spontaneous and random. The examiners will be looking out for those 2 words. Spontaneous meaning it's not affected by external factors. So if you heat up your radioactive sample, it doesn't matter. It still decays just the same. And random means we can't predict which individual. You've got a sort of batch. You've got a sample of radioactive nuclei. Say, you've got, in reality, you have trillions and trillions. But even if you had a batch of 100 in a little baking tray, there's no way of predicting which one's going to pop next. So that's talking about individual nuclei. But what you can do, you can model the population as a whole. You can't predict which one's going to pop, but you can definitely predict that one of them is going to pop at some point. And you can predict when it's going to pop. Not necessarily exactly, but you can say in the next half-life, half of them are going to pop. The decay constant, lambda, is the probability that a nucleus will decay in 1 second. So in the next second, what's the probability that a nucleus will decay? We measure radioactivity as activity in decays per second. And the unit is becquerels, which is not an easy name to spell, but it's shortened to BQ, so we don't need to know how to spell it. The activity is equal to lambda n, but recognize that because activity is the decays per second, each decay means the population n. So n is the number of undecayed nuclei. Every time a decay happens, n decreases. In other words, A is equal to minus dn by dt. It is the rate at which our population is decreasing. And would you look at that? We've got another linear differential. We've got a differential equation. We need to find n as a function of t such that its differential is equal to itself with a negative sign. What function fulfills that criteria? It is the exponential function equals itself when you differentiate it. If you put a negative constant upstairs within the function, that will take care of this negative down here. Again, you don't need to do A-level maths to do A-level physics, but just content yourself that you have this differential equation, its solution. All the solutions are of the form, mathematical form, this. Okay, what does this look like? We've graphed it here. It's an exponential decay where you start with an initial population, n0, and it never reaches 0, but it decays pretty quickly. The time, another curious feature of this particular graph is that the time for the number of remaining nuclei, n, so at any time, it doesn't necessarily mean the start only, to halve is constant. So the time to get from n0 to n0/2, let's call it the half-life. By the time a second half-life passes, it'll have halved again to n0/4, and so on and so forth to an eighth, a 16th, a 32th, etc. Yep. This is not a property of all decays, so this is specific to exponential decays. Okay. What then? How does this relate to our decaying constant there? We've got this relationship here. Where does that come from? Well, if you take our decay equation and you set n equal to n0/2, what you're asking is essentially, well, how long does it take for the population to halve? If you solve this equation, so that n0's factored out, you take a logarithm of both sides, the natural logarithm, so ln half is equal to minus lambda t. Ln of a half is also equal to minus ln 2. So t, and this is a specific value of t, bear in mind, t a half. T 1/2 is equal to ln 2 over lambda. Okay, voila, QED. So this is the graph for the remaining undecayed population. Now, the curious thing is we said that the activity is equal to minus dm/dt, but we've just solved an equation saying that this decay function, when you differentiate it, it equals itself. So this is a graph of n, but the graph for A takes a similar shape. So not only, so the population decays, but also the rate at which it decays. So wrap your head around that. They may have different starting values though, of course. A0 and N0 are not guaranteed to be the same. Okay, so let's put this into practice. A sample of 800 atoms of X decay over time. Into atoms of Y with a half-life of 3 years. On the axes provided, plot a graph of N, the number of atoms of X in the sample, against T, the time in years. Okay, so choose a suitable scale. Plot is our command word. Make sure that your scale envelops a sensible stretch. Okay, so if the sample halves every year, first of all, we've got to fit 800 on here. We've got 1, 2, 3, 4, 5, 6, 7, 8. So we can fit 800 up here. Like so. And we want to get a decent number of half-lives in, 4 or 5. So it's worth provisionally working out a few values: 800, 400, 200, 150. You could have fit in maybe one more point here as well, if you like. And then draw a nice curve through them. I'm glad I don't have to attempt that with my graphics tablets. But in the exam, do your best to draw a nice curve through all of them. Okie dokie, nice question. Nuclear physics. Right, so we're talking about annihilation. We're saying if you get an antiparticle, particle, smash them together, and you produce two photons. Why two photons? Because you need to conserve momentum. You had two particles that, yes, they had opposite charges. One was anti-particle, one was particle, but they both have mass. There's no, even antiparticles have mass. They don't have anti-mass or anything like that. It's, it's all mass. And Einstein's famous equation shows that there's an equivalence between mass and energy. You can convert between the two. And this is one of those instances. C, speed of light, 3 × 10 to the 8. That's a huge number. And then you're going to square it. So for 1 kilo of mass, you're getting a gargantuan amount of energy. So mass is essentially very, very concentrated form of energy, which is a very tempting proposition for, nuclear reactions. There's no wonder why we were so keen to crack open the atom. So it implies that any change in the mass of a system is accompanied by a release of energy. Yes, that is true. Binding energy, we'll see in a bit, manifests itself as a change in mass. So consider an electron and positron, both of mass 9.11 × 10 to the minus 31, annihilating to 2 photons. The change in energy before and after is the change in rest mass, mc². So we had 2 × 9.11 × 10 to the minus 31. That's pretty tiny still. Times 3 × 10 to the 8², which is, of course, 9 × 10 to the 16. Plug that into a calculator, and I got 1.6398 × 10 to the minus 13 joules. You might say, so what? That's tiny. But that is literally only 2 electrons, not even atoms. An electron and a positron. The head of a pin will contain trillions. So there's plenty of energy floating around. All of that energy is going to form 2 protons, and the energy of to say protons, I meant photons. The energy of a photon is Planck's constant multiplied by its frequency. Okay, so that was mass. That was the annihilation of mass to produce energy, but a slightly more subtle version of the interaction between energy and mass is when we talk about binding energy. I always struggled to understand this when I was a student, actually, binding energy. So let's pay close attention to definition in the red box. The binding energy of a nucleus is the total work that must be done to separate a nucleus into its constituent nucleons. Okay, so a nucleus is bound together, which in itself is a bit of a mystery because you would have thought all these positively charged protons were aching to get apart, but no, there is a force stronger than electromagnetism, and it is the strong nuclear force, and that's keeping the nucleus together. That force has to be overcome, so you need to put in some work, tear it apart, and then suddenly, if you remove all your constituent nucleons far enough away from each other, they won't have an effect on each other, so remove them to infinity. That total amount of work done, that's the binding energy. The mass defect then, actually, before we move on to the mass defect, so I've just done a bunch of work to separate. If I've done a bunch of work separate them, that implies I've put energy into the system. That's correct. Where has it gone? It's increased the potential energy of all these particles. And when we're talking about electrostatic potential, these are, protons, they repel each other. Therefore, if I'm doing, actually, no, sorry, forget the fact they're protons. They are all nucleons and they are bound by the strong nuclear force. That's the key operating. And so when they're in the nucleus, they sit in a potential well. And it's a well that you need to get them out of. And so in removing them all to infinity, I have to put in a certain amount of work. And that is the binding energy. Okay. It feels odd to me, and it maybe feels odd to you, that the binding energy is defined in this way in this sentence that is talking about tearing things apart. You'd think it would be better called the tear apart energy or something. But yep, all the work I'm putting in to separate them results in an increase in potential energy. Why potential energy? Well, because at any point, if the band got back together, if they reunited, work would be done by the fields to bring them back together. So that work can potentially be used, hopefully. If I'm giving them all energy, it means that the mass is going to increase. And the mass defect is the difference in mass between a nucleus and the sum of its constituent nucleons. So the sum of masses here is greater than the united mass of the nucleus. Okay, so it's this mysterious process where you have a nucleus, you crack it open, and if you put all the constituents on a measuring scale and weigh them individually and add that all up, you end up with a bigger number than when you started. Why? Because I've put in energy, and energy and mass can be interchanged. Okay, the mass defect is associated with a release of energy. Yep, I agree. So let's put this to the test. What is the change in mass? My final mass is 6 times, oh golly. I told you that the mass of protons and neutrons was similar. It's 1.007, 1.008. So, there you have it. Okay, there's your final mass. Your initial mass is just this 13.00336. That is equal to, the change in mass is equal to 0.10101 U. Okay, so the change in energy is the change in mass times c squared, which is 0.10101 times U, which is 1.66 times 10 to the minus 27 times c squared, which is 9 times 10 to the 16. Put that all together and you end up with 1.51 times 10 to the minus 11 joules. Okay, so that's one nucleus. If you split it apart, you get something on the order of 10 to the 11 minus 11 joules. You might again think, oh, that's tiny. In electron volts, considering an electron volt is 1.6 times 10 to the minus 19 joules. So you're talking something on the order of 100 million times larger than an electron volt at such a small scale. It's pretty powerful. So don't underestimate it. Okay, exemplar exam question. Calculate the difference between the energy required to break a sulfur-32 nucleus into 8 alpha particles and into its individual nucleons. Okay, it's a very similar question to what we've just done, but this time, I don't have to write anything because it's all pre-written for me. Okay, so the change in mass, you finish the first. If you're splitting it just into your alpha particles, your final mass is 8 alpha particles. They subtract the original mass. You get a mass defect of 0.04 U. And the energy gained, multiply it by c squared. You get not quite as much energy as last time, roughly about half as much. 5.9796 times 10 to the minus 12 joules. Okay, how about if we split it even further into the individual protons and neutrons? Yep. So bear in mind, they didn't actually tell us how many protons and neutrons were in sulfur 32, but it told us it broke down into 8 alphas. We know each alpha has 2 protons, 2 neutrons. Okay, so we can do a bit of deduction. Break it down, and instead of 0.04 U, you get 0.284 U. 0.04 U. Okay. So you've gone from effectively 4 to 28. So that's going to be a 7-fold increase, which is awesome. Or 7-fold multiplication, technically. Sorry. Calculate the energy released, and we're back up to the level of 10 to the minus 11. Great. What's the difference in energies between these two reactions? Oh, look, it's a numbers game. If you didn't have your calculator for that question, I would feel very sorry for you. Okay, so we are comfortable now, or more comfortable, with the idea of binding energy. It's the work done to pull these atoms apart. But protons and neutrons don't generally like existing on their own. And so the options we have are to start with really big atoms, pull them apart, and then allow them to recombine into smaller nuclei. And that's fission. So you start with uranium-235, which is a huge nucleus. You split it apart with a neutron. That takes loads of energy. You have to do work to do that. But when they recombine, they release loads of energy, and they release the trade-off you are then seeking to make is that you are hoping, so uranium-235 will be all the way out here. The daughter products, the results, will be up here. I forget off the top of my head what they are. What you are hoping is that the energy you've put in here to split up uranium-235, the binding energy per nucleon, you want, when you recombine to form the daughter nuclei, you want to release more energy per nucleon. So you want to start from somewhere down here and end up here. So fission can theoretically work for any nuclei in this region where the red arrow is of this diagram. You're essentially squeezing a bit more binding energy out of each nucleon. But even so, you can see from the diagram that the difference in binding energy per nucleon is not huge on this side. The advantage of fission is that you're starting with some pretty unstable nuclei to start off with. And so ultimately the energy you put in to break these nuclei is not too hard to come by. Far harder to break up the really stable nuclei like hydrogen 2. But what scientists have been working on for many years, and are slowly making progress, but they can't promise anything basically, is fusion. And if you can imagine, you start with a bit of heavy hydrogen down here, and you could break that and maybe form something way up here. The difference in binding energy per nucleon is going to be gorgeous, potentially way larger returns on your investments in terms of energy. Right. Enough sort of general waffle about fusion and fission. The binding energy per nucleon, yeah, it is essentially a measure of the stability of a nucleus. And so if you look at this graph online, you'll also see, we've depicted it as this nice smooth curve, but you do get sort of jagged peaks and stuff, but you have islands of stability. Heavy hydrogen is, for example, is less stable than H2, which, there's actually a peak here and so on and so forth. And dead in the center, we see that the most stable nucleus is iron. And that's why at the center of the sun, you have a core of iron. The sun starts with loads of hydrogen. It fuses to helium, fuses on and on and on until the end product is iron, which can neither be fused in an energetically favorable way, nor can it undergo fission in an energetically favorable way. Right, isotopes, and the key dividing line is then this nucleon number of 56. Anything with a nucleon number of 56 would ideally fall in the fusion category. Anything with a nucleon number bigger than that would be fission. Yep. Okay, I wasn't off when I put my uranium, and technically I said this was uranium-235. So, well done to me. Uranium-238 is all the way out here. But for now, we've got to concede that nuclear fission is our main source. We can't realistically achieve fusion quite yet, or we can achieve it, but not in an energetically favorable way. Nuclear fission, heavy radioactive nuclei undergo fission, and this process you do need to know a bit about the practicalities of it. We're not going to cover what the sort of control rods are, what the setup of an actual nuclear reactor are. Those do feature in your syllabuses there. So you'll need to go away and revise that. But at a microscopic level, the process goes as follows. You launch a single neutron it's what we call a slow-moving neutron or a thermal neutron. The reason we call it thermal is because it's moving at speeds that you could traditionally associate with regular Brownian motion within, a room temperature room. It needs to go at that speed in order for this to work. You launch it at uranium-235, it breaks up, the protons and neutrons recombine into their more energetically favorable, more stable dorsal nuclei, and we've got krypton and barium, and you produce 3 further neutrons, which are slowed down by your coolant, and then go on to hit other uranium-235 nuclei, and the whole process snowballs. Any points I missed from these bullet points? The energy released, is equal to the changing binding energy. That's the total binding energy, not the binding energy per nucleon. You use uranium-235 as a fuel. Good. Whew, I thought I panicked when I saw uranium-238 on the previous slide. And the neutrons released by fission can go on to induce more fission in a chain reaction, which is great in the sense that it sustains itself, not so great in the sense that it can get out of control. That's what the control rods are for. You place them and they absorb some of those neutrons so that they don't go on to trigger fission in other reactions. Okie dokie. Looking at my slides, we're actually very near the end. Sweet. So nuclear fusion. As I say, we can achieve this, but we can't do it in an energy efficient way at the moment. Some light nuclei can undergo fusion, or at least can't do that on a industrial scale that's useful socially. Some light nuclei can undergo fusion. Remember the shape of our graph. So we're talking when we say light nuclei. The ones we're most interested in are really early on in this scale of nucleon number, but theoretically, anything with a nucleon number less than 56 could do it. Fusing together to form a larger nucleus, more stable nucleus. Remember that binding energy per nucleon is a measure of stability. So I could even label this axis stability. And it's more energetically favorable to you achieve a lower total energy state if you have more stable nucleon. Okay. The difficulty with fusion is you then need to you're not trying to split apart you're not trying to split apart a huge nucleus. You're trying to put together two small ones, and to get them close enough is pretty hard. You've got electrostatic attraction to overcome, and you need to get those two nuclei far closer together than is the case in a large nucleus. A large nucleus is already pretty large. The protons at the extremis and the nucleons at the extremis are already pretty far apart. But you've got 235 of them all in one place. Whereas here, you've got a grand total of 6 nucleons, and you've got to force those together right at the center of the scrum. Close enough for the so you've got to overcome the electrostatic repulsion. Protons getting close to each other, they're all positively charged. But if you achieve sufficient closeness between them, a strong nuclear force will kick in and overcome the electrostatic repulsion. Okay, what does this look like? If we combine 2 protons, we can form a hydrogen 2 molecule. That's nice. If we add a proton to a hydrogen molecule, we can form this heavy hydrogen, which is used as a fuel for fusion. Also, by the way, note that this is a beta positive decay. Because during this process where we smack 2 protons together, one of the protons becomes a neutron to form the hydrogen. And then finally, once we've got this helium, sorry, I think I called it heavy hydrogen, but it's close to the end of the day. Helium-3, get 2 of these, smash them together, and we're aiming to craft ourselves our very own good old helium-4. The offshoot will be some extra protons, which can then be used to start the process all over again. So unfortunately, unlike fission, where there's really only one nuclear reaction going on, you put a neutron in, the fireworks kick off, and it produces 3 neutrons, which can then go on to trigger other ones. Here you've got at least 3 different processes going on all at the same time. And you want to do this not on a sort of per atom basis, but you want to do this, a whole bunch of them all together. Okay, exam question, final one of the day. Stars are formed when protons are brought together under intense pressure so that they can overcome electrostatic repulsion and collide. Correct. Explain how these collisions cause the star to produce energy and atoms with larger nuclei. Okay, so we're talking about fusion. Hopefully, from the context of the question, you'll be thinking that as you read it, as soon as they talk about stars and stars being formed, it's going to be talking about fusion. Okay, it's an explain question, so we like just to state a few facts, 2 physics facts and maybe a linking statement, or maybe 1 fact and sort of progress it from there. So we start. 2 protons are brought close enough together by intense gravity. So explain how does the star overcome electrostatic repulsion? In this case, it's gravity, just because the star's like so large. As I said before, gravity is relative to the other fundamental forces pretty weak. But if you have enough mass, you can basically do anything. Intense gravity is that the attractive strong nuclear force overcomes electrostatic repulsion. So already they've deployed some extra physics terms outside the question. Causing nuclear fusion. Yep, let's be explicit about what's going on. Although I read that into the question, the question itself doesn't actually use the phrase. So take advantage of that, by all means. The fusion reaction turns the two protons into a single larger nucleus. That is correct. And this nucleus has more binding energy per nucleon. Perfect. Meaning energy must be released during the fusion.